Hi everyone, Mr. Lee here. In this video, we're going to do modified Atwood machines. Now, modified Atwood machine is just like a regular Atwood machine, except that one of the masses is on its surface rather than hanging free. So let's call this M1, and M1 is attached by a rope across a frictionless pulley. Okay, and the rope goes over, and on the other side we have another mass, and we'll call this mass M2. So this is a modified Atwood machine. Now usually both masses in a Atwood machine are free hanging, but in this modified Atwood machine, one of the masses is on a flat surface. Alright, so let's dive into how to solve these problems. The very first thing that you want to do is you want to create a free body diagram for both masses. So I zoomed in on here so that you can see what I do for M1. I'm going to do M1, yeah, let's do it in green. Alright, so because we have a surface, the very first thing that we're going to draw is the normal force, and the other one will be the force of gravity. Okay, so we have two forces there, normal force and the force of gravity. And if there was friction, we would include friction, but like for the sake of this problem, I'm going to say there's no friction. All right, now we have a rope here, and because we have a rope, we have this thing called a tension force, and the rope will be pulling on this object to the right. Okay, now let's do the other object. I'm going to do this one purple. So we have a hanging object here. Because there's no surface, the very first force that we're going to draw is the force of gravity, and that force of gravity is going to go straight down. And we do have a rope here, and because this rope is all the same rope, we're just going to call it T. Now you can call it T1 or T2 or whatever you want, but that's just T. All right, so we have our free body diagram. Now, the very next thing that you want to do is you want to make sure everything is moving along the same axis. So I'm going to pause right here. So this is a free body diagram. So if a problem asks for free body diagram, this is what you give them. But in order to actually solve for this situation, we need to do a little bit more, just like what we did with the Atwood machines. So the first thing that you want to identify is what is the axis of motion. So we know that M1 will be sliding across the table along the x-axis. And it's easy for me to just swing M2 up so that M2 is also moving along the same horizontal axis. Let me show you what I mean over here. So I'm going to redraw everything as if everything is moving along the same horizontal axis. So we have M1 here, we have the rope, we have the pulley, and remember I swung up the mass, and so we have M2 over here. Okay. All right, so this is our new rotated modified Atwood machine. Okay, so the reason why I do this is because now M1 and M2 are both sliding along the same horizontal axis, whereas before here M1 moved along in the horizontal axis and M2 moved in the y-axis, and we don't want to do that. We do not want to do that. We want to make sure everything moves along the same axis. Okay, so if I were to do my free body diagram, M1, nothing's changed. So I'm going to do the free body diagram for M1. We have the normal force going up, we have the force of gravity going down, and we have the tension force going to the right. Cool. Next, we have the modified or the altered free body diagram over here. So here we have tension going up, but you see here how we swung everything in a counterclockwise fashion. So what this means is that when T was originally just going straight up, because we swung everything out like this, instead of going up, tension is now going to be going to the left here, like so. Okay, and so this is a good base, right? Because ropes can only pull. So this rope is pulling on M2. Okay, ropes can't push. All right, the next thing is to do FG. So if T, the tension, is going straight up, and straight up means that it's pointing to the left, that must mean down must be pointing to the right. So we have FG2 right there. So I'm going to write FG2 over here, just so that we can be consistent. Okay, so here we have our new modified Atwood machine. Okay, and we took it a step further, and we got a free body diagram, and we made it so that both objects in the system are moving in the same axes. Next, what we want to do is we want to create a net force formula. Okay, and we're going to look at it in the horizontal motion because that's the motion that the object's going to be accelerating in. All right, So stream strategies, what you want to do is you want to ask yourself, is this object or is this force along the x-axis? So I'm going to start off with m1. Okay, f of n, it's not t. T is. I'm going to put that down as positive t because it's pointing to the right. F of g, that's in the y-axis. Here we have t over here, but that's negative t because that's pointing to the leftward direction. And then we have positive fg2. And we have this formula right here. Now, for those of us that saw it, all right, tension and tension, they cancel out. So that leaves us with Fg2 is equal to max, all right? So this is really cool. So what this shows us, we could break this down even more, excuse me. We can say that mass 2 times acceleration due to gravity is equal to m1 plus m2. Now we want to make sure we have both masses there because this mass represents the system as a whole, and so that's m1 and m2. So we can see that the only force that's actually accelerating this entire system is the weight component, of the hanging block. That's it. That kind of makes sense, right? Because the force of gravity is the only thing that's pulling everything down. It's dragging everything down, and we see that within the equations here. Okay, and so if we wanted to find the acceleration, all we would have to do is divide both sides by m1 and m2. Okay, so depending on what the problem is asking you to do, and that would leave us with a sub x is equal to m2g divided by m1 plus m2. So that's one of the ways that we can use this equation. I'm going to highlight this equation because this is the equation that we want to focus on, right? We want to be able to get to that part. m2g is equal to m1 plus m2 a sub x, because from there we can arrange the variables however we want. Right, and this is an example down here where I arranged the variables so that we had the acceleration of the system. All right, next we can also find the net force in the y direction. Now this is cool because we see that the accelerated motion is in the x direction and not the y. So that must mean that the acceleration in the y direction is zero. Okay, and that just makes our lives so much easier when the accelerated direction is in only one direction. So we have f of y is equal to 0. Now, what we can do now is look at the free body diagram and we can figure out what the y forces are. And in this case, it's the normal force and Fg. I'm going to write that as Fg1 for clarity purposes. And so over here, we can write that we have f of n minus Fg1 is equal to 0. We could break this down even more and say f of n minus m1 times g equals 0. And boom, right there. Right there is as good as it gets, right? And from there, we can break it down even more, and we can say that the normal force is equal to m1g, and we can, go forth from there to solve for different things. All right, so the next thing I want to show you is how do we find the tension. Now, in the previous Atwood machine video, I showed you how to find the tension, and in this case, it's no different. The steps are the same. But just in case, we'll go over it one more time. So in order to find the tension, okay, let's say we wanted to find the tension here for M2. So we're taking a look at M2. Let's do this in red. I want to find the tension of this system right there. Okay, I want to find the tension of that system. So in order to find the tension, you must identify one object within the Atwood machine, because as we saw over here, where it has T minus T, normally the tensions cancel out. So in order to avoid this problem, we look at one object. Okay, so I'm going to redraw what I circled over there on my left. I'm going to redraw that down here. So we have M2. Up is T and down is Fg2. All right, so now we have a isolated object, and from there we can create a new net force equation. Okay, and this one will be in the we'll just make it just the y direction, right? So we have the net force is equal to ma. All right, we don't have to care about the x's or the y's in this case because there's only one direction. And so we have positive t minus Fg2 is equal to, now normally we would make this M1 plus M2 because there are two objects in the system, but notice here I'm only looking at M2 because I've isolated that system. I'm only looking at one object here. Okay, so this would become our equation. Now, in order to find tension, so by the way, like this is where you want to be at. Okay, so once you're there, you can arrange all of these in whatever fashion in order to find your whatever we need to find, basically. So from here, if we wanted to find the tension, we had to isolate tension so that it's the only variable left. So we can say that tension is equal to mass 2 times the acceleration, that's the acceleration in the system, plus Fg2. Okay, now we can break this Fg2 down even more, and we can say that the tension is equal to mass 2 times the acceleration plus mass 2 times g. Okay, all right, now up here we found what the acceleration is for the entire system. And so the next step is to get whatever we found up here and substitute it in for our acceleration. And it'll look something like this. T is equal to m2 times all of this. Okay, so I'm going to write a big parentheses, m2g divided by m1 plus m2, parentheses, okay, and parentheses there. So what I wrote right there, I'm going to write it below, that's our acceleration. I substituted all of this into this big bracketed parentheses plus m2g. All right, and there you would plug in your numbers and you will get to a final answer of exactly what was our tension. All right, well, that's it for me. I will see you next time. Bye-bye.